Everyone, good afternoon, as the case may be. My name is Joe DePoe. I'm part of the technical pre-sales team for Neo4j in our London offices. And today, I'm giving a presentation called Making Graph Algorithms Click. What we're going to try to do over the next half hour is understand a few graph algorithms. And we're going to do this using the medium of classic teen films. So what we're going to cover, first we'll do a quick introduction to the label property graph model and Cypher, just to make sure everyone is on the same page, so that when we look at the demo, it makes sense. We'll take a quick look at the graph algorithms from Neo4j that we have available, and specifically the two that we'll be looking at today. We'll look at PageRank, and we'll use the film Heathers as the data set that we run against PageRank. Then we'll look at a separate example from Mean Girls, a different film using label propagation. And then we'll have some time at the end for Q&A, and there'll be a few questions that you'll be able to answer as well based on what we've seen. So first, I'll apologize to keep it authentic and to respect the source material. There'll be a lot of 90s teen speak. So I love these films. You'll have to excuse me if I get a little excited, a little carried away, and start talking like a Valley girl. And also, if you care about these sorts of things, these are very old films, so hopefully you've seen them, but we will be revealing the plot of some of these movies, so there are spoilers ahead. So quickly, as I said, first we'll talk about the anatomy of a property graph database. So we all know what we're talking about when we look at some of the data. This is the label property graph model that Neo4j implements. It's based really on three different things. So first we have nodes. Nodes here are circles. They represent things, entities, nouns in our database. Here we can see our nodes are labeled, and we have two different labels for these nodes. And we have two person nodes and one car node. Labels are just that. They're ways of labeling a node. If you come from a relational database world, a relational background, nodes may kind of feel like tables, but a label doesn't imply a schema. And what I mean by that, so we have some properties associated with these nodes. Properties are just key value pairs. The node on the left, we can see has a name property of Dan. Dan was born May 29th, 1970. We have his Twitter handle, which is @Dan. The person on the right has a name property of Anne. She was born December 5th, 1975. We don't have Anne's Twitter handle, and that's okay. It's not like in a relational database where you have to put a null value into that column. We don't have her Twitter handle, no big deal. If we get it later, we can add it very easily. Likewise, if we get her Instagram handle, we don't have to add one for Dan for Instagram. So it's quite flexible, schemaless or schema light out of the box. Although you do have the ability to add these kind of constraints, if you want unique indexes or nodes to have particular properties on them, you can apply these sorts of schema constraints. So those are nodes, those are properties. Lastly, we have relationships. And this is really what makes Neo4j quite different from other databases. We see here we have a loves relationship from Dan to Anne. We have a loves relationship from Anne to Dan. So every relationship in Neo4j is persisted with a direction. And sometimes that direction is important and sometimes it's less important. So loves is a really important direction to understand in your graph, because Dan could love Anne, but it would be possible that Anne doesn't love Dan back. So fortunately for him, she does, but we have two relationships here to show that they love each other. Whereas we only have one lives with relationship, because if Dan lives with Anne, then of course Anne must live with Dan. It's kind of logical that way. So we can choose at query time to ignore the direction of the query because we don't really care which way it goes in. We know there's only one of them, and it's you can kind of treat it as bidirectional. And you can see you can also have properties on relationships as well. So Dan drives this car. He has since January 10th, 2011, although it's Anne who owns the car. So those are nodes, relationships, and properties. And these few components are really what allow us to build these kind of really robust, complex models and reflect all the context that we need to be able to work with the data in our graphs. And then quickly, just a brief introduction to Cypher. So Cypher is the query language for working with graphs that Neo4j has created and implemented. Some of it will feel a bit SQL-like if you're familiar with SQL. Match is sort of like a SQL select. We're defining the pattern that we want to match in the database. It's meant to be very graphical, kind of like ASCII art. So nodes are round. As you see here, we have the same nodes as we had before. Dan, who loves Anne. So we draw the node that we're looking to match using parentheses. So it looks like a round node. We give the label that we're looking to match. So here we're looking for a person node, not a car node. And then we give, in curly braces, the key value pairs that we want to match. So we're looking for a person node with a name property of Dan. Then we draw the relationship. So Dan loves someone. So the direction is drawn using this dash and the greater than sign, right? And then we put another node at the end. He loves someone, but we don't know who. So we put this variable in, beloved, and then when Anne's information comes back from the database, it gets populated into that variable, and we could work with it later in the query to access the properties that are on Anne's node. I mentioned before that we can ignore the direction at query time. So if we wanted to see who loves Dan, we could move the greater than sign and put it over here as a less than sign, and that way you would change the direction of the relationship to see who it is who loves Dan. And if you wanted to see in both directions, both who Dan loves and who loves Dan, you could just get rid of the greater than altogether. You have a dash at either end of the braces, the square braces, and that would tell the database that you want to match the relationship in either direction. So a bit of a whistle-stop tour, but hopefully as we get into the demo, anyone who's not as familiar with Cypher or hasn't used Neo4j before, this will give you kind of a basic level of understanding what we're going to be looking at. So quickly, graph algorithms. We have over 35 of them now. These are graph algorithms that we have implemented for use in Neo4j. You can see down in the bottom, there's a URL here. If you follow that, that will take you to the documentation, the latest documentation for all of these algorithms. They are available as a free download. It's just a jar file that you drop into your plugins directory in your Neo4j install. Or if you're using Neo4j desktop, it's even easier than that. There's a button that you can push to install the graph algorithms plugin for your database, and away you go. You call these as functions, and we'll see how that works in a little more detail in a bit. The algorithms are broken down into 5 main categories. So there's pathfinding, and anyone who's used Neo4j before is familiar with the shortest path or the all shortest path functions. They work based on the shortest path is defined by the number of hops that you're following. So if you traverse 5 relationships, that's a longer path than if you traverse 2 relationships. These pathfinding algorithms are really more focused on weighted pathfinding for the most part. So sometimes you'll have a property on a relationship that gives it some sort of a weight, and that might be distance, physical distance in space. It could be time, it could be cost, any number of different things. And so sometimes you might have a graph where the shortest path in physical distance, according to the weight on these relationships, the shortest path is 10 hops long. And you could have another path that's only 2 hops long, but is much longer in physical distance. Right? So we're looking for the shortest path by adding up all the weights of the relationships we're traversing. We're not going to look at any of those today. We are going to be looking at one of the centrality and importance algorithms, which is PageRank. So centrality and importance, these algorithms look at how to identify within your graph what nodes are important or the relative importance of each node in your graph, and it can do this in a number of ways. So the centrality algorithms really look at things like what nodes sit on the shortest path between the most other nodes. PageRank, we'll get into more detail in a little bit of how that works. Next is community detection. So these algorithms look for clusters of nodes, groups of nodes, communities of nodes in your graph. We're going to be looking at label propagation, which is one of the community detection algorithms, but there's quite a few in here. Louvain is quite a famous one, and I use triangle count quite a bit, actually, in the context of social networks as well. Then there's similarity. So similarity algorithms compare nodes to each other and determine how similar they are based not on some properties on them, like doing a text comparison of names or something like that, but instead looking at the structure and the graph around these nodes. If nodes are connected to many of the same things, they have many of the same neighbors, then this may give you a certain degree of confidence that they're very similar, or maybe they're the same. So very useful for things like entity resolution, as well as working with data quality issues. And then there's link prediction, which can predict whether two nodes should be connected in the graph or whether they may be connected in future. Again, by looking at the similarity in the graphs around them. So two people who have lots of the same friends but aren't directly connected in the graph may have a relationship between them. You might predict that these people do actually know each other because they have so many of the same friends. It's likely they've met before. So again, down here on the bottom right, would recommend that you take a look, read through the documentation. We also have on our website, neo4j.com, you can download, we wrote an O'Reilly book on graph algorithms, and it's available as a free download from our site. So I would encourage you, if you really want to get into a lot of detail, it's a great book. You can download that and have lots of examples and lots of detail on how to run the algorithms. For now, we're going to take a look at PageRank. And we're going to do this by using characters from the movie Heathers. So Heathers was released in 1988. Big film with Winona Ryder and Christian Slater. I quite like it. It's from a particular time in my life, I guess, from my formative years. Maybe it doesn't look exactly like my high school, but quite familiar. It's quite a dark comedy, and it features themes of murder and suicide, which we're not going to touch on today. But in 1988, in a pre-Columbine world, maybe it actually was quite insightful. It's set in Westerberg High, which is a snapshot of late 80s teen culture. There's lots of cliques. There's jocks, there's cheerleaders, there's dweebs, and then there's the Heathers. So the Heathers are the stars of the movie. They're not all actually named Heather. There are 4 of them, but there's 3 Heathers and 1 Veronica who are part of the group. And they're the most popular girls in school, and they rule the social scene at Westerberg High. And what we're going to try to do is figure out why they're so important. How can we use the graph and the PageRank algorithm to quantify why they are so popular? So first, just to touch on PageRank and how it works. PageRank is an iterative algorithm, and it was named after Larry Page, one of the founders of Google, because Google uses it as a way of ranking web pages in their search engine results. And the idea is that, traditionally, maybe web searches would just look at how many times a phrase appeared on a web page. And this was quite easy to trick. You could put the same word lots and lots of times on your web page, and you go up in the rankings, right? Very easy to fake. The insight behind PageRank is that important pages are more likely to be linked to by other important pages, right? So what we're measuring then is the transitive influence or connectivity of nodes, which means that if you're connected to by important nodes, then some of that importance rubs off on you. Okay? And if we're looking at this kind of in machine learning terms, this would be a regression algorithm, right? So PageRank assigns a score along a range, along a continuum. So every node will get a score It's not a classification algorithm, which is what we'll look at when we look at label propagation. But because we're looking at this idea of transitive influence, popularity and importance rubbing off on the neighbors of a node, I think it's interesting and maybe quite useful to think of this as a high school popularity contest, right? This is kind of how high school works. Popular people have popular friends. If you're not popular, if you're a nerd or a geek, you could have 100 nerd friends. That doesn't make you popular. Whereas having just a couple popular friends would actually make you much more popular, right? And so again, at the bottom here, we have a link to the specific documentation for PageRank where you can see all of the different parameters, get some more information about when is a good use case to use PageRank, when isn't. And this diagram will explain a little bit more about how this concept of transitive influence works before we take a look at the graph. So you can see there's lots of these little green circles down here that all point to this bigger blue circle, right? So if this is our graph, these are unimportant nodes, but because they all point to this node, it gets a boost because it's linked to by these other nodes. But then, because it has some built-up importance from the links that it gets from these other nodes, its links make the nodes that it links to automatically more important, right? So some of its importance rubs off. So you can see this nice big yellow circle here doesn't really have as many links maybe as some of the other ones do, but because it has links from important nodes, bigger nodes, it becomes more important in our graph, right? So the way this works, PageRank, the algorithm iteratively goes over the graph. It can either distribute a node's rank over its neighbors, or it can count how many times during random walks a particular node is traversed. But the idea is that as it iterates over the graph, it develops a clearer picture of how this importance, how this popularity moves through the graph, and it will iterate over the scores that it assigns until it reaches convergence equilibrium or is good enough, at which point you get your score. So we'll see how that works. This is the browser, the Neo4j browser. We'll look at the data for the Heathers graph here. So this is broken down into a couple clicks. You can see it's quite densely connected. The Heathers are up here in this kind of orangey color. You can see there's 3 Heathers. There's also Heather McNamara. She's pink because she's also a cheerleader. We have some loners over here. So Jason Dean is the newcomer to the school. He's a bit of a bad boy. He ends up getting involved in some of the darker aspects of the plot line. He really likes Veronica Sawyer. She really likes him, but he doesn't really have many other friends. He's a loner. And then we have another loner who has no connections, poor Martha Dunstock, who's the tragic hero of our film. She doesn't really have any friends, so we would expect her PageRank to be quite low. Then kind of working down, we can see a bit of a social hierarchy. So there's jocks, there's cheerleaders, the posh kids, the country club kids, the yearbook club, the geek squad, the dweebs, and then down at the bottom, we have the metalheads and the stoners. This just kind of generally reflects the stratification of high school society at Westerberg High. There's a lot of relationships going on here. So what we see are maybe the stoners and the metalheads like each other. They're jealous of the posh kids because they have a lot of money and nice clothes. Everybody is kind of jealous of all the men are jealous of the jocks. All the girls are jealous of the Heathers. And then you have some kind of quite specific relationships that will have an interesting effect on our PageRank. So, for example, Veronica likes Betty Finn. So even though Betty Finn is a dweeb, Veronica and Betty were really good friends when they were young. And so they have this friendly relationship. And we'll see what that does to Betty's PageRank score when we start looking at how some of that transitive influence from Veronica rubs off on her. So calling the algorithm is quite straightforward. It's quite easy. I have the query saved here. So we're calling the PageRank. We're streaming the results back to the browser. So we could write back to the database, which is what we'll do when we use label propagation. But here we're just streaming the results back. So we're doing a calculation and then getting those results right back to the browser. We're just doing it on Heather's nodes. So both of my demo data sets, both from Mean Girls and Heather's, live in the same physical database. So all of our nodes have more than one label. Here we're just looking at Heather's nodes, and then they would have an additional label like Heather's or Dweeb or what have you. We're passing in a few parameters, and we'll see what tweaking these can do. So first we're going to start with 3 iterations, 3 passes over the database to run our calculation. We're using a weight property on our relationships. So not all of our relationships are created equally. For example, the Heathers like each other, but they're more like frenemies, right? They don't really like each other. So the weight that we've given that is 4. Whereas other people who are genuinely friends with each other, the weight on that likes relationship is a 10. And then there's some other differences, like if you're envious of someone, that might make them more popular if everyone's jealous of them, but it's not a really strong weight to that relationship, right? So not as strong as like if you really like someone. If you want to date someone, that's quite a strong weight. So many of our relationships will have varying weights, which gets taken into account when we run our page score, our PageRank. There we go. So we can see these are our results. Heather Chandler, she's the queen bee of the Heathers. Naturally, it makes sense that she would be first, followed by Veronica Sawyer, Heather Duke, and Heather McNamara. And we can start to kind of see some of that social stratification appearing even just in our score. So Heather Chandler has quite a high score. When you start getting down into the cheerleaders and the jocks, they have lower scores. And then as we move down through the posh kids, the yearbook club, the geek squad, and so forth, we can see that kind of gradual decrease in popularity scores. But I think what's interesting is we can take a look at how different iterations can affect those results. So if we just do one iteration, rather than going over numerous times over the graph, we'll just go one pass, and we can see Veronica Sawyer ends up with a higher score than Heather Chandler. Right? And this is because by doing more iterations, you get a clearer view of how everyone's actual score weighs in. Right? The graph can't know everyone's score straight out of the gate. It has to do some recursion to understand that transitive influence as it moves through the network. So the more iterations you do, you can expect your results maybe to be more accurate, right? So the default for this is actually 20, I think. And we can see if we run that, we should get some more accurate results to the graph. Now, of course, this is quite a small graph and quite easy to do these sorts of calculations on. On a much bigger graph, doing a huge amount of iterations could be quite time-consuming, right? So it's a bit of a trade-off. The lower number of iterations might run faster on a big graph, but may not be as accurate or may not have reached convergence in its results. you might get a more accurate score if you run lots of iterations, but then you can expect that, on a very large graph maybe to take a bit longer. So moving on, we'll take a look at Mean Girls. So Mean Girls was released a bit later than Heathers. Came out in 2004, starring Lindsay Lohan and Tina Fey. We're going to look at label propagation and how we can identify cliques in our graph using label propagation. So the film is maybe less dark than Heathers, but no less biting. It still has kind of a strong story to tell. It's based on a screenplay. The screenplay is based on a nonfiction book called Queen Bees and Wannabes, which talks about social cliques in high school and the damaging effects they can have on girls in high school. It's set in North Shore High School, which is in Illinois. And again, it's full of cliques. And the thing with these cliques is they all sit at different tables in the cafeteria at lunchtime. The most popular clique are the Plastics, much like the Heathers. Probably not terribly nice people, but very.
Okay, so hopefully you can see my screen again. So we're going to use label propagation to find the cliques in our graph. The idea behind label propagation is that it uses network structure alone as its guide, right? So we're not looking at properties on any of the nodes or on any of the relationships. We're just looking at the structure of the graph. It doesn't require any information about the communities in advance, although there are ways that you can seed the labels that it will use. But we're not going to be doing that. We're just going to look at communities in the graph. This is part of our community detection group of algorithms, as we said before, but this is a classification algorithm. So it's not scoring things, it's classifying things. So we're going to end up with a number of communities that are just defined as community 1, community 2, but each of our nodes will be classified as being a member of that community. And this is how we're going to find cliques in our graph. So first, I have to restart my database, which shan't take very long. So while we're waiting, I know we've overrun, so to give people a chance before they have to drop off, there are some questions that we have for the Hunger Games quiz. There are 3 questions. These are the ones that you can see here that you can answer, and we'll come back to these in a bit. Now my database has started. So first, we'll take a look just at some of, we'll take a look at the Plastics. We'll take a look at what some of the cliques look like, right? So here we have the Plastics. They're all friends with each other. If we drill into one of these Plastics, so Katie Heron, the new girl in school, who becomes a Plastic rather quickly, we can see there are lots of people who like her, right? So here we have some desperate wannabes who always wear the fashions that the Plastics wear. They all like Katie, but they're friends with each other, right? So we have these kind of individual communities, people who are friends with each other, and then they have some other relationships with other people. So they might, the jocks bully some of the other kids. Lots of people like other people. What we're looking for is clusters of people who are friends with one another. And to facilitate this, you can see now we've got all of our labels from the different groups in the cafeteria. So there's freshmen, there's the JV jocks, there's the sexually active band geeks. We've labeled all of these as we created the data so that I could see who I was working with. Now we're going to erase all of that. We're going to trash all of our labels from the Mean Girls data set. And then we're going to try to reproduce them, right? We're going to see if we can identify the plastics algorithmically. So you can see now, if we go back, all we have are our header labels. All of our labels from the Mean Girls data set are gone. We don't know who our groups are anymore. And what we're going to do is call label propagation. Really straightforward. We're using Mean Girls nodes. We're using the friends with relationship, and we're writing back to a property on these nodes called community. Right? So very straightforward. What that will do is start pushing labels through the graph. Every time it goes through an iteration, a node will get the community assigned to it that is based on the majority of connections from its neighbors. Right? So the graph starts moving around labels, playing with what communities each node belongs to until it reaches equilibrium, where every node has a community as determined by kind of the majority of its connections. Right? So if we take a look again at our plastics here. Oh, no, we don't have plastics anymore. We'll pull up some of our Mean Girls. So here we have Katie Heron again. And we'll see Katie is in community 7. If we match all of the you'll see these are our plastics. So Gretchen Wieners, Karen Smith, Regina George, and Katie Heron have all been put into community 7, right? So they were originally labeled as plastics. We took that label away, but we managed to put them back into the same community they were in before using label propagation, right? So we've detected these clusters of people within our graph based on who they're all friends with. And again, this is quite a small data set, a small example, but if you can imagine doing this against millions of nodes, if you're a retail store, maybe looking to create communities of people based not just on some kind of metric like their age or their gender or what have you, but based on their physical connections, right? So it's quite an interesting way of leveraging the graph to build community, to build a view of communities in your graph. So with that, here are the Hunger Games questions again. Apologies for our little tech hiccup. I appreciate everyone who stayed with us. I'm in the QA channel now, so if there's a few minutes left, if anyone has any questions that haven't been answered in the chat, I'd be happy to give it a go. Michael, if you're still with us as well, are there any questions that have come up that I need to answer? Okay, maybe not. Well, thank you everyone for joining. I hope you found this interesting. I hope everyone understands a little bit more about graph algorithms more generally and specifically at the ones that we've looked at today. You'll have seen at the beginning of the presentation, I'm quite easy to find. Joe DePoe on Twitter, on LinkedIn. There aren't many Joe DePoes in the world, so I'm easy to track down. If you do have any questions, do feel free to reach out. And I hope you all enjoy the rest of the presentations. Thank you.